Welcome back for another code.Pylet tutorial. In this video we're going to be looking at images and how to display, move, rotate, scale and animate them. So first off, let's get down to the basics and understand how an image is drawn to the display surface when we supply a set of coordinates. Here you can see the image is drawn so that the top left corner is directly over the X and Y coordinates. If you wanted to centralize the image on X and Y, you'll need to subtract half the image width from the X value and half the image height from the Y value. We can see how this is done in this script, which simply loads an image and places it in the center of the display surface. The same information I've just mentioned is also available at the top of the script. So how do we load images into our Pygame script? Well, to be honest, it couldn't be easier. Take a look at this line here. We call Pygame image library and use the load function to load our image. One of the good things about Pygame is that it supports a number of image formats, namely JPEG, PNG and GIF, and the load function determines which image you're trying to load by the file's extension. Once the image has been loaded, it is then stored in the myImage variable. As mentioned previously, sometimes we may want to centralize the image on the X and Y coordinates, and to do that we need some information about it. If you already know the dimensions of the image you've just loaded, then great, define a variable called image width, image height, and assign the appropriate values. If you don't know the image dimensions, then you can call the getRect function and it'll give you that very information. It'll even give you the center, or as I like to call them, half values of the width and height. Essential when you want to centralize the image to the X and Y coordinates, as I've just mentioned. So this is what I've done here. R now contains the width, height and center points of our image. Let's now look at how we display the image to the display surface. Because DS is defined as our display surface, it has some functions which allows us to draw an image to it, and this is called blitting. You can see here that we're calling our display surface's blit function with the first parameter being the image we would like to draw onto it. In this case, we'll be using my image, which we got from loading the color wheel 100 PNG. The second parameter is a set of X and Y coordinates enclosed in brackets, which are used to tell the blit function where to place the image on the display surface. Remember, R contains the dimension of our image and also the center values as shown here. Center 0 contains the value of image width divided by 2, and center 1 contains the image height divided by 2. So when we deduct those values from half the display width and height, the image will be displayed in the middle of our surface. So let's run the script and see if that's true. Yep, the image is in the middle of our display surface. So that's how to simply draw an image, but what about if we want to move it? So now we're going to be looking at our second script entitled Moving Blit, and let's scroll straight into the action and have a look at what's different. We're still loading the same image, color wheel 100 PNG, and getting the dimensions of it. Because we would like to move our image on the display surface, we need some way of keeping track of its direction and position. This is why we set up two variables called direction and X. In this script, the image simply bounces from left to right across the display surface. So really, we'll only be adding direction to the X coordinate. So how does the direction variable determine which way the image will travel across the display surface? When we first run the script, direction is set to 1. This means every time we cycle through the main program loop, we add 1 to the horizontal position of the image. Remember, a horizontal position of 0 is located on the far left edge of the display surface. So adding 1 to that value will move it closer to the far right edge. If we change direction to -1 and add that to the horizontal position, the image will move to the left. The starting value of x is in the middle of the display surface. Now let's have a look at the main program loop. Again, we are blitting my image to the display surface. But what's different in this script is we're now passing the value of x to the blip function to affect its horizontal position. The vertical position, on the other hand, remains the same. It's still in the center of the display surface. It's all well and good passing the x value to the blip function, but we need to change the value of x to see the position of our image change. And this is what we're doing in this line. Remember, on the initial running of the script, the value of direction is 1. So every time this line is executed, we're adding 1 to the position of x. But what happens when the image gets to the far right edge of the display surface? Well, it'll simply keep going right. You won't be able to see it, but its position will still be increasing. What this means is we need some kind of mechanism to change the direction of the image once it reaches the edges of the display surface. That could be the far left edge of the display surface or the far right edge. So this is what we're detecting in the next line of code. We're checking here to see if the value of x is greater or equal to the display width minus the width of the image. In this script, the display surface width is 1280 pixels and the image width is 100 pixels. So if x is greater or equal to 1280 minus 100, then swap direction. We also need to swap direction if the value of x is equal or less than 0. We can change the value of direction by multiplying its value by -1. Because 1 times -1 is -1, and -1 times -1 is 1. We then update the display so we can see the changes we've made by blitting. And then clear the display surface so we can start over. I'll show you what happens if we don't clear the display surface on each cycle of the main loop after we run the script as it is now. So as you can see, the image moves from right to left and vice versa. So now let's see what happens if we don't clear the display surface on each loop. We now see trails of the color wheel because we're not removing the previous blitz of the image. So now let's have a look at bouncing multiple images all around the display surface. So in this script, we're still going to be using the color wheel 100 PNG because it's bold and bright and its size makes it ideal to use in videos. But look, we've got a new section in this script and it's called data tables. A data table is, as the name suggests, a table filled with data. This table is filled with direction data, 360 degrees worth of data to be precise, and each entry in the table has two parts. The first is the direction value needed to affect the x coordinate, and the second is the direction value needed to affect y. For example, if I wanted a ball to travel 90 degrees from its current position, then I'd look up entry number 90 in the data table and add the first part to x and the second part to y. And what we'll see is the ball travelling in the desired direction. It'll be easy to show you using the little script I wrote to demonstrate this very data table. The white lines represent 360 degrees and the 360 entries in the data table. The purple line shows which entry in the data table we'd like to use, and as we move the mouse about the display surface, the selected entry changes. You can also see the direction value for that selected entry in the data table. If we go to entry number 0, you can see that dx is 1 and dy is 0. If you add those values to a set of x and y coordinates, then an object would simply move to the right. If we go to entry number 90, you'll see that dx is 0 and dy is 1. And adding these values to an object's position would make it travel straight down. With this script, you can move the ball that's in the center of the display by pressing the left mouse button, and it will travel in the direction selected in the data table. Because we're using multiples of the same object in the script, it's easier to create an object class and use it to build a list. I'll quickly go over this class and what it does. So here, we've defined the ball class and created two floating point variables called x and y. Obviously, this will represent the position of the ball on the display surface. When we first create a ball object, Python calls an initialization function, and what this does in this case is assign some random values to the location of the ball and its direction. The direction value is a random number between 0 and 359 and represents 360 degrees. We then use that number to get the direction value from the data table I mentioned previously. The draw function in this class blits the color wheel 100 PNG image to the primary display surface, centralizing it on the x and y coordinates. The move function adds the direction values to the ball's object position, then checks if the ball hits the left or right side of the display surface. If it does, then the horizontal direction value swaps polarity, meaning if the direction value is 1, then it becomes -1. This also applies if the ball object hits the top or the bottom of the display surface, but instead the vertical direction values swaps polarity. So now we're getting closer to the main loop, and it's time to define the ball objects. N balls is how many balls we'd like to make, and balls is the list container for those objects. So in the main loop, we iterate through the list of balls, assigning b to the ball object as we go, and then calling that object's do function, which I skipped over in the class definition. What this function does is it calls the object's move function and then the draw function. So essentially, just a cleaner way of doing the move and draw functions. So, to the bit we've all been waiting for, let's run the script. And there you have it, 20 balls bouncing around the display surface. So that's simple blitting done, but what if we'd like to change the image in some way? Now let's have a look at rotating an image. We load an image in the same way and ask for its dimensions. In this script, we have two functions, rotate and rotate and center. They both do the same thing, except rotate and center draws the rotated image centralized on the X and Y coordinates. So let's delve into rotate and center and find out what's going on. When calling this function, there are 5 parameters we need to pass to it for it to do its job properly. The first identifies the surface that we want to draw to. The second and third are the X and Y coordinates. The fourth is the image we'd like to rotate. And the fifth is the number of degrees to rotate by. When we call the transform library's rotate function, it creates a new image. The image you specify in the parameters is merely copied and is left untouched. The newly created rotated image is then stored in the variable rotated. Because this function centralizes the new image to the X and Y coordinates, it's important for us to know the dimensions of the image, primarily the center values of width and height. These values are deducted from X and Y coordinates to centralize it. The rotate function does the same thing, creates a rotated copy of our image and draws it at X and Y. When using this function, the top left corner of the image is located at X and Y. So before we run the script, let's have a look at the setup variables and the main loop program. So we know that this script will be rotating an image, so we need a starting angle. The best place to start is probably 0, so we'll assign that value to the variable degrees. And that's the setup done. Moving down into the main loop, the first thing we do is call the rotate function. We're rotating the image that we loaded earlier to an angle stored in the degrees variable, and the location of the image will be drawn to the primary display surface. We're also using the same parameters to draw a centralized version of the same image, but in a slightly different position. Then lastly, on every cycle of the main loop, we increment the angle by 1 degree. If the angle is greater than 360 degrees, then we reset it to 0. It's worth noting that if you specify a value greater than 360, then it doesn't matter, because a value of 361 degrees is the same as 1 degree. Now let's run the script and see what happens. The first image is placed with the top left corner over the X and Y coordinate, and the rotation looks a little strange. This is because the width and height of the object changes as the image rotates. The centralized image, on the other hand, looks like a rotating object should. It doesn't matter if the width and height change. So let's have a quick look at another script which combines multiple rotating images, a data table, and a 2-frame animation. I'm not going to explain this script, but you can download it from my Google Drive with all the other scripts featured in this tutorial. So let's run it and see what it does. The Tesla balls bounce about the display surface. The bounce height decreases every bounce until it reaches a minimum height, then bounces to the top to start over. It's worth noting that they also are centralized on the X and Y coordinates. So we've rotated an image, but what if we want to shrink or enlarge an image? That's going to be the topic of this next script, scale.Py. Because we've covered most of this script already, it's worth getting stuck in and scroll down to the setup variables. What we'll be doing is growing an image until it reaches the size of max scale, and then shrinking the image until it reaches min scale. And then start the whole process again, forever. Because the size of the image is dynamic, meaning it can be changed at will, we need to use a variable to store the size of the image and adjust the value of that to alter the size of the image. The variable we're using for that purpose is called the current scale. So we know the image gets bigger and then smaller, but how does the script know how to change the value of the current scale? Well, we use the direction value that we add to the current scale variable to change its value. If the scale direction is 1, then the size of the image increases. If it's -1, then it shrinks. In the main program loop, we test current scale against max and min scale and swap the polarity of scale direction. So let's have a look in the main loop. Remember the rotate function? It was part of the transform library. Well, so is scale, and again, as with rotate, it doesn't alter the original image. It creates a scaled copy. In this example, we're storing the new image in the variable scaled. The parameters of the scale function are as follows. The first is the image we'd like to scale, and the second are the new width and height values we'd like the new image to be, enclosed in brackets. Here we're using the value of current scale for both the width and height, so the enlargement remains a square value. It's really that easy. As usual, we blip the image centered to the display surface. The next few lines show the mechanism behind the enlarging and shrinking process. Here, we're adding the scale direction to the current scale and testing if it has either reached the maximum scale or the minimum. If either tests are true, then swap the polarity of the scale direction. So let's take a look at the script in action. The image grows and shrinks just as you thought it would. So that's scaling an image. But what if you'd like to animate it? In my opinion, there are two effective ways to animate an image in Pygame. The first is to load a sequence of images into a list, and the second is to load a single image containing all the frames of the animation and displaying the portion of it that corresponds to the frame number. Let's have a look in more detail at each method. Let's start with the list method. What we do here is load each image using Pygame's image library and store it in the list. So as this image depicts, catwalk 1 PNG is loaded into the list index 0, catwalk 2 PNG into index 1, and catwalk 3 PNG into list index 2, etc. Then, when we want to display an image from the list, we can simply pass the part we want to the blip function. The way we animate the sequence is to use a variable to index each image in the list and increment it on each iteration of the main loop. I'll show you an example of that in a bit. Let's go to the partial method. This method involves loading a single image, like we see here, catwalk PNG, and only displaying a portion of it. In this example, catwalk PNG contains all the frames of the animation. It has a height of 2400 pixels and there are 12 frames. So if we divide 2400 by 12, we'll know the individual height of each frame, which works out at 200 pixels. If we want to display a portion of an image, then we add a third parameter to the blip function. This contains the dimensions of the portion we'd like to display. In the code here, we're displaying frame 5, So 5 times 100 is 1000. That means frame 5 has a vertical offset of 1000. The last two parts of the frame's dimension are the width and the height. Just like drawing a rectangle. So if we wanted to animate this image, we'd use a variable to reference the vertical offset within catwalk PNG. So let's have a look at some code. So following on from the partial animation method, here we load the catwalk PNG and get its dimensions. Getting the dimensions is important because we need to divide the image up into equally sized frames. We know that there are 12 frames to this animation, so we create a variable to reference that number. We can then use that variable to find the individual frame height. Frame height equals image height divided by frame count. The next line is a little more complicated because what we're doing here is creating a list of rectangles, and each rectangle references a frame within catwalk PNG. So the first rectangle in the frames list has the dimensions 0, 0, 400, 200. The second is 0, 200, 400, 200, etc. Only the vertical offset is changing for each rectangle. So if we go back to this image, we're basically building a list of these dimensions. X and Y offset, width and height. The starting frame of the animation will be 0. So when we blip the animation to the display surface, you can see here that the third parameter of the blip function is the dimensions stored in the frames list, indexed by the frame variable. Remember, we're actually passing the whole catwalk PNG image to the blip function, but just displaying a portion of it. So now let's have a look at the other animation method, loading individual files into a list. Because our images are in separate files, we need a way to load them into our list. We could write out a huge list of loads like Pygame load catwalk 0 PNG, Pygame load catwalk 1 PNG, etc. But that would just take time and you'd have huge chunks of image load in your script to scroll through. So instead, if each file is numbered like catwalk 1, catwalk 2, catwalk 3, we can create a list dynamically with a for loop and use the variable to reference that file name. In this line of code, as we iterate through the for loop, we're replacing curly bracket 0 with the number referenced by I, and at the same time loading the image into the list. Because all the images in the sequence are the same size, it doesn't matter which image in the list we use to get the dimensions. So now when we do the blitting, we pass the entire image to the blip function from our list and use the frame variable as the index. I didn't mention in the last script that the frame variable needs control measures, because if the value of frame is greater than the number of items in your list, then you'll get an error and the program will exit. So here you can see if frame becomes greater than the frame count, reset to 0. So let's have a look at the script in action. I'll just point out that both animation scripts produce the same output. So here it is. And that concludes this tutorial on images. I hope you found it useful. And if you'd like to download these tutorial scripts, you can just follow the link in the description to my Google Drive. For this particular tutorial, I'd recommend downloading the entire folder because it contains loads of images. Thanks for watching, and I hope to speak to you again very soon.